recording. Let's say that. Okay, well, is it recording? Yeah, so we are live. So again, I was saying earlier that anyone who wants to succeed in calculus 2 really needs to be on top of things with these substitutions. And I'll do some more substitutions today, and then we'll move on to something else. But remember, this is the thing that you want to pay attention to. All right. So if you have any questions, let me know. Otherwise, I'll start over here with the substitutions. Let's see. There's apparently no questions. All right. So here's one more substitution, and then we'll move on. So let's do something like number 20. So I'll do one more substitution. Number 20 of section. I marked a lot of these problems, but I did them, not necessarily in increasing order, so I got confused here of 4.5. The reason why I didn't do them in increasing order is that they're not uniformly organized. So this is one type of substitution, this is the second type of substitution, and so on. So they kind of skip here and there, and we saw that there's two types really in calculus 1. This is one of them. So 20 of this says calculate the integral x square root of x plus 2 dx. Now, so here's the deal, folks. So this is just a review. Again, that's not it's not more difficult or anything than the other problems. So just so you remember, so again, when you start these kind of problems, recognize again a power and some derivative, right? A power of a function, some derivative. In this case, well, there we go. X plus 2 to the 1/2 is the square root that you see here. And then move x and dx to the other side. And let's see if that works by the thing that we did there. So this almost does, except there's a trick here. So I said this is not more difficult. Actually, it is more difficult. So this is one of the problems that's slightly more challenging than the usual one. So yes, it makes sense to do the substitution u equals x plus 2. And then do the derivative, du equals, and we will see that that is the same as dx, 1 times dx, right? So there's nothing really there to worry about except that we have x dx, which is not necessarily a derivative. So here's the trick with this problem. We're going to write this problem as and we're going to say here, so you know what, when we substitute, we're going to say the antiderivative of u to the 1/2 times, and now instead of x, I'm going to solve for x from the first one here. Normally we solve from the second one part of the substitution, but here it's possible to actually solve for x from the first one. And we're going to say, you know what, x was u minus 2. And dx itself is very easy because that's the same as du. So we're going to change it that way. So this is, again, a substitution problem, but this is with a trick. So I'm not sure if I would put a problem like this, maybe for a bonus on a test or something, again, and I don't think you would see these kind of things even in calculus 2. So there's other tricks there, but this is the type of trick that it's in between. So in between the routine problems and the trickier ones. So over here we're gonna write the antiderivative. Let's do the calculation. U to the 1/2. So distribute here. That's going to be u to the 3/2, u to the 1/2 times u, right? And then minus 2u to the 1/2. This is going to be du, and when we calculate the antiderivative, this is not too difficult. So this is simply, folks, for u to the 3/2, we'll say u to the 5/2 here times 2/5 minus, and for 2u to the 1/2, we'll say u to the 3/2 times 2 times 2/3. All right, so this is going to end up being finally 2/5. Remember the substitution u was x plus 2 for u. So the formula is x plus 2 to the 5/2 minus 4/3 times x plus 2 to the 3/2. All right, this is our answer. You can put a C if you fancy a C there constant, but this is our answer for the corresponding problem. So that being said, folks, this question again, this question would be in terms of difficulty. If the other ones that we did up to this point would be, I would say, in terms of difficulty, 6 or 7 out of 10 in terms of difficulty, then this one over here is significantly more difficult than those. So I would say an 8 or a 9 in terms of difficulty. There's more difficult questions again, but those you will deal with in calculus 2. So that being said, let's do something else. So let's do the following. We are going to move on and do some definite integrals. Now you might say, well, didn't we already do definite integrals? Why do we have to worry about those? Well, I'll show you in a second. So here's a problem. The first problem here, number 35 of section 4.5, says do the not the antiderivative, but rather the integral from 0 to 1, a definite integral of cosine of pi t over 2. So what's this thing here, pi t over 2 dt, right? That's the problem. Well, folks, when you see this kind of problem, of course, every definite integral problem, remember the fundamental theorem of calculus says to do an antiderivative. And this is what we're going to do here. So we're going to do the antiderivative first, and then we are going to evaluate that from we're going to evaluate that from 0 to 1. So we need to do, and in colloquial terms, people say we drop the bounds first. This is kind of, that's kind of how you do it, because dropping the bounds is the same as saying antiderivative. So folks, this being said, we're gonna do that, and we are going to get the following. The integral of cosine of, and I'm going to write here pi over 2 times t dt. All right, what is this thing here? This is an antiderivative. And this antiderivative needs to be calculated with the methods specific to antiderivatives. So before we calculate it, we're going to use a substitution. That's the reason why these guys are putting this kind of problem in the section with a substitution rule. Because when we calculate the antiderivative, we're going to be forced to do a substitution. The substitution u is pi over 2 times t. Du, notice how pi over 2 is just a constant, so du is going to be pi over 2 times dt. And if you want to solve for dt, like we said in the previous problem, we solve for t, but we don't have to here. So here we have to solve for dt. That turns out to be 2 over pi times du. All right, so this is what we're going to use in the calculation, because my formula now becomes cosine u times, and dt, folks, is 2 over pi times du. All right, and this is easy to evaluate, so it's 2 over pi times the antiderivative of cosine is sine u. Or in my case, 2 over pi sine, and we said that u was this guy, so pi over 2 t. All right, so this is what we evaluate here, folks. when we evaluate the integral, we're going to go straight up here and we're going to say, you know what, the integral that I started with would now be this one, evaluated at the numbers 1 and 0. So it would be 2 over pi times sine of pi over 2 times 1, which is just sine of pi over 2, minus 2 over pi sine of pi over 2 times 0, right, which is sine of 0. Now this turns out to be 0, and this turns out to be 2 over pi. Sine of pi over 2, by the way, is 1. So, so the whole answer to this problem turns out to be 2 over pi. So, so we can say that the answer to my problem is 2 over pi for the integral. So the integral, the area that we're looking at there is 2 over pi. All right, so remember that you could potentially see integrals like that, and that's actually what's going to look like in calculus 2. You're going to get integrals, definite integrals that you want to evaluate, and you want to do some sort of substitutions even with both. There's another method with definite integrals to carry the bounds throughout the substitution, but I'm not going to cover that because this is just enough. And I don't think you will use that in calculus 2, although there might be situations when your teachers might want to review that method. So, but I'm not might want to explain that. It's not a big deal, but I don't want to confuse you because again, that people get confused and they have two methods and they wonder which one should I use. Well, this one, if you use it properly, it will lead to success 100% of the time. So next problem. I'm going to do the number 37. So we'll do some problems here, a couple more, and then I am going to move on to areas between curves. So number 37 of section 4.5 says calculate this one, integral from 0 to 1 of the root, and the root is here the cube root of 1 plus 7x dx. All right, the exact same situation. So this is an integral of something complex. It really is the integral from 0 to 1. Actually, I'm not going to rewrite it. So so we'll come back and we'll write. Oops, come on, give me the pen. We'll come back and we'll write what it is when we get to calculate the antiderivative, but of course the focus will be on the antiderivative. So drop the bounds, folks. Yep. So to use the fundamental theorem of calculus, you need the antiderivative, and rewrite this as, instead of cube root of that, so I'll say 1 plus 7x to the 1/3. This is the equivalent way, and somehow this got mixed up here. So and this is going to be dx. All right, folks. This thing goes by a substitution. So u equals 1 plus 7x. Du is equal to 7dx, the derivative, right? So, all right. So over here we have the antiderivative of 1 plus 7x to the 1/3. Okay, so that's going to be the antiderivative of u to the 1/3 times, and dx, folks, there we go. We solve for dx. From here, dx is 1 over 7 du. So this is the thing, and we're gonna put that in here, and that's gonna be 1 over 7 times the antiderivative of u cubed is u to the 1/3. I'm sorry, u to the 1/3 plus 1. So that's gonna be 4/3 times 3/4. So this is gonna be 3 over 28 times. And u was 1 plus 7x, so 1 plus 7x to the 4/3. All right, this is the one. This is the one. This is not the answer to my problem. This is the thing that I'm going to use in here. So I'm going to substitute 0 and 1 in this formula, starting with 1 because we subtract, right? So this is going to be 3 over 28 times 1 plus 7, which is 8. I could set that to the 4/3 minus, and then 3 over 28 times 1 plus 0, 7 times 0, right? So it's going to be 1 plus 0 if you want to the 4/3. And these numbers can be calculated easily. You can use a calculator, obviously. I don't have one right now handy, but I can do that in my head because look here, 1 plus 7 turns out to be 8. To the 4/3 is 8 to the 1/3, which is the cube root of 8, or 2. 2 to the 4 is 16. So that's going to be 3 times 16 over 28. 3 times 16 over 28. There's some simplification here, but I'm not sure if I'll get any from this term. Let's see, this is 3 times 1. 1 to the anything is 1, so minus 3 over 28, and that's going to end up being 3 times 15, or what's 3 times 15? 45 over 28. All right, so 1 second, folks. All right, so it's 45 over 28. Okay, this is the answer to my problem. So the answer is 45 over 28. All right, so this is another substitution problem. And finally, you can do some more complex questions here. And there's a few that require a little bit of cleverness. I am going to do one such example again. This is very much in line with what we did earlier in a previous problem. So, so this is, if you want, a repetition of problem 1 today, or problem 20, that is. Okay, so here's the problem. So now pay attention to this one, x square root of x plus 2. Okay, so now let's see this one here, folks. So this is number 47 of section 4.5, and this is the one that I'm going to end up with. So it's an integral from 1 to 2 x times the square root of x minus 1 dx. All right, folks, so now let's pay attention here. So that previous problem was x square root of x plus 2. This one is x square root of x minus 1. There's no significant difference between them. In fact, if you pay attention here, it's just a different constant that I add under the square root here. But other than that, it's exactly the same type of problem. So I'm going to write the integral here without bounds again. I'm going to write, instead of, so x times x minus 1 to the 1/2 dx, or the other way around, x minus 1 to the 1/2 times x dx. And I'm going to say here, well, this is going to be a substitution. So u is going to be x minus 1. Du, the derivative is going to be dx, so the derivative of x minus 1. And this is going to be over here. This thing is going to be over here. The antiderivative of, and I'm going to put u instead of x minus 1, u to the 1/2. And now over here, we have to replace not only the dx, which is du here, it's very easy, but also dx. So we're going to have to look at the first part of the substitution, and we can easily see that because x minus 1 is u, x would be u plus 1, just add 1. So I'll have u plus 1 here, and then I'll also have a du over here instead of dx. So it's very easy to figure that thing out. Now, now this thing here is the following thing. So it's going to be equal to, so let's do the calculation. So first let's distribute. So u to the 1/2 times u is u to the 3/2 plus u to the 1/2 du. And that is nothing but, a simple antiderivative, u to the 5/2 times 2/5 plus u to the 3/2 times 2/3. So, so this is all there is, and then we can write in terms of x, obviously, 2/5 times, and u was over here, folks, x minus 1 to the 5/2 and there's 2/3 times, and the other one u is again x minus 1 to the 3/2. All right, folks. So this is going to be the antiderivative. Now this guy is the one that I'm going to take and I'm going to substitute in here. I'm going to use in here. So substitute what? Substitute 2 and 1 in this formula. So we'll have 2/5 times 2 minus 1 to the 5/2 plus 2/3 2 minus 1 to the 3/2, and then minus, and then substitute 1 in the formula. Now when I substitute 1, I get 0. So we can say 0 here and just get rid of that. And even better, now we see that this is going to be just 2/5 because 2 minus 1 is 1, to any power is still 1, plus 2/3, and that's going to be 6 plus 10, 16 over 50. All right, folks, so this is going to be our answer for this particular problem. And I'm going to move on to something else. So answer is 16 over 50. Okay, so this is the last problem that I'm going to do here for substitutions. My recommendation again is, and as I said earlier, after you go home and if you want to watch these videos, I saw that there's some activity. So there's a number of people who watch these videos online. So when you go home, maybe you want to, so for instance, for a lesson like today's, you want to stop the video once the statement is, you see the statement on the board, and you want to work out the problem yourself and then see how far you go. I think this is very important because even if you don't get them right, you still are going to figure out something useful, and that's going to be the step where you get stuck, and then you investigate why you got stuck there and you learn. So that's kind of a learning process. If we were in a face-to-face situation, I would have said, okay, so do this independently, or if we had the recordings available ahead of time, then I would also say, watch the recording and then let's do one. Let's see how that works. So if you want to do a flipped classroom. All right, so this being said, let's move on to number 5, applications of integration. That's going to be, number 5, chapter 5. Actually, section 5.1. Applications, chapter 5, folks. Chapter 5, section 5.1. So let's say chapter 5, applications. Oops. Come on. Applications of integration. All right. And 5.1 really is areas between curves. All right. The examples that they give us in the book are, some of them illustrative, some of them are difficult. So let me sort this out for you folks. The problem here, the problem that we address here is the following. Let's say, oops, let me move this, make this a straight line and another straight line here. So let's move it this way. And let's assume we have some curves here. So there's one and there's another one. There we go. So let's say we have some sort of fish here on the screen. And you want to calculate the area between these two curves. So, so what do you do normally? Well, so what you would do, folks, you would want to look comparatively, you would want to look what's under them. Now, the problem is that if you look carefully here, one curve goes above the other one and there's an intersection. So you want to pay attention to where that intersection point is. So you would split up the area into a bunch of smaller areas where clearly one curve is above the other or something like that. And then what you would say, you know what? I can calculate the area under the curve because that's what Riemann taught us. So Riemann taught us, let's say this is the function f, this is a function g. So Riemann taught us to have the integral of f of x dx, for some bounds, let's say a and b here, and then subtract, so that's the area under the graph of f, which I'm going to color here with, oops, I clicked on the wrong thing here, with red. So you have this big area with red, and then you're going to subtract the area with blue, which is this one here. So if you eliminate from the red area, eliminate the blue area, you get what you need in terms of the integral. So you get the integral from a to b over here, subtraction a to b of g of x. So f of x minus g of x, and that is, folks, the result of this. So this is the area that we have over here. So that's the area of the fish, the body of the fish. So what you see here is we're not doing anything very clever, really. We're just using what we have in terms of definitions, in terms of integrals. So this integral can be written as an integral, if you want to write a compact way, f minus g dx. I'm not even going to write f of x dx minus g of x or something like that. I'm just going to write f minus g. And you may wonder, but how do I know which one is on top and which one is at the bottom? Actually, it's either by inspection, by looking at the picture, or using the idea of absolute value. Because if it happens that by mistake you took one, you took the wrong one at the top, and then the other one will be also wrong because it would turn to be the bottom, fake bottom. So what you do here, you're basically switching signs here, really, folks. You're doing g minus f. So that's not so essential to the big problem. What you could correct that problem by simply taking the absolute value of f minus g. But some people still don't like to work with absolute value. So provided, folks, provided that you end up with the correct corner, so you figure out which one is on top and which one is at the bottom. The integral that we're looking at here, this one here, is simply, so even if you get a negative result, you're still okay because all you have to do is to drop that minus sign. So you can still calculate f minus g, basically just randomly choosing which one would be at the top without even drawing the picture. But again, the important thing is to find the corner. So you can do g minus f and you'll still be fine. Just remember to drop a negative sign. So if the question, folks, pay attention here. So if a question is asking for the antiderivative for the integral for the area, and it doesn't say oriented area or something like that, it just says plain area, what you want to do, you want to pay attention here. So you want to subtract the top and the bottom of your area, right? You want to subtract those two, and if you end up with a negative number, make sure you throw out the minus sign. So that's a basic point here, because areas, folks, are positive numbers, pretty much like volumes are. When you do the same thing in calculus 3, you will discuss about volumes. Now, examples of areas, maybe you don't see that often in practice unless you measure the area of your house. I don't know how many 100 square feet or something like that. But volumes, you work with them very often. So whenever you put gas, you put 2.5 gallons or something like that. Or I don't know, so something like that. When you buy milk, you buy a gallon of milk. So you use volumes all over the place, really, in real life. And as volumes, it's common sense that they cannot be negative. You can define a negative oriented volume if you want, but in practice, they should not be negative. And if some problem is asking for the plane volume or the plane area, in this case, you want to say, well, so this is the number. That number should always turn out to be a positive number or zero. So you cannot put negative 5 gallons of gas, because that wouldn't make any sense. So it's like that with the area. So pay attention if a problem is asking for the plane area. We'll do volumes a little later too. Then make sure that you get the positive value of that. And also the corners, pay attention to the corners of the picture. So this is all my discussion about areas. Now let's do some concrete calculations. And there's a number of problems that are very interesting here. I'm gonna do example 1 from the book. So this is example 1. We're gonna do more examples next time. So I want to make sure that there's a number of people who don't usually attend class on Tuesdays for whatever reason. So I want to make sure that at least those will get to see this again, the opportunity to see this again tomorrow. So it says here, find the area of the region bounded by above by y equals x squared plus 1, below by y equals x, and to the sides by x equals 0 and x equals 1. So you see they describe the picture very clearly here, so we know what to do here, folks. All right, then let's see what this region looks like. So I'm going to sketch that by hand. It's not so terribly difficult, but if you want to see how to do this with Desmos, and I'm going to do this with Desmos if we have a little time here. Oops, not that, I didn't want to do that. So 1 second, folks, let me select the correct thing. So here's what the picture looks like. All right. First of all, I know what this is. Y equals x. Y equals x is this kind of line. So hold on a second. Why does it not give me straight line? There we go. So that's y equals x, folks. All right, so now I'm in business. That's y equals x. Now, this is the bottom of my picture. Y equals x squared plus 1 is going to be the top of my picture. So that is a parabola that looks something like this. And finally, x equals 0 is this vertical line, and x equals 1 would be something like this. So this is x equals 1, this is x equals 0. There we go. This is the thing that we are looking at. So y equals x squared plus 1 is the top, y equals x is the bottom. So this is what we want to calculate. And I tell you what, the picture was harder to draw than the problem itself, because the problem itself is really an integral. So the area that we want is an integral from 0 to 1. So we're looking on the x-axis, folks, always, where the picture lies, right? So 0 to 1. And the next thing that I'm going to say here, I'm going to say the top, which is x squared plus 1, minus the bottom, which is y equals x. So minus x dx. And this is a piece of cake for us to evaluate. Let's do the integral of x squared minus x plus 1. It's rewriting this thing, dx, without any bounds. That means the antiderivative, right, folks? This is what we learned in the previous lesson. So this is simply 1/3 x cubed minus 1/2 x squared plus x. Take that and plug in here. So plug in 1 and 0. So you get 1/3 times 1 minus 1/2 plus 1. And then minus 0. And that's going to be 1/3 minus 1/2 is going to be negative 1/6 plus 1 is going to be, what is that going to be? 6 minus 1 is 5/6, folks. All right, so that's the answer to this particular problem. Now, if you want to do the exact same thing and you want to do this with decimals, at least to get a clear, accurate version of a picture, it's going to be similar to this one, but of course, nicely scaled. We can open decimals, and I'll show you how to do that with decimals in a second. So let's do decimals. Sometimes Desmos has been pretty reliable, folks, but you know, on the test, you may want to make sure that you download the app or something if you want to use it. So remember that the curve was y equals, the first one, y is equals x squared plus 1. There we go. The second one was y equals x, so we said the bottom. The left side is x equals 0, I'm sorry, and the right side is x equals 1. So anything that's in between these two, these four, is my picture. And you can see the corners are nicely formulated here. This is a beautiful picture, and there we go. So these are the corners. This is my picture, the one that I evaluate here. Now, interesting enough, Desmos can do calculations of integrals. So, for example, I can do integral by simply typing the symbol, the letters int from integral, or select the symbol. There's a symbol here somewhere. I think there's a function or something. No, doesn't. There is an integral. So typeset, okay, there we go. So I don't know how to do that, but I know how to do the integral. So typeset the int again. Let's delete that. So oops, wait a second. So int, there we go. The integral, it gives you the option to put a lower bound. So the lower bound is 0, and then the upper bound just up arrow 1. And over here, we're going to put the quantity x squared plus 1, right? That's the first function minus the second function was x dx. And that's going to be, so let's see why it doesn't let us do this. That is interesting. Well, you know what? I think there is a symbol here somewhere. Okay, so it doesn't let us do that for whatever reason. Let me figure out. So why it wouldn't let us do this thing? Maybe change to T here. The letter doesn't like the letter or something. Squared. Oops, not that. T squared plus 1 minus t dt. Yeah. Well, still doesn't like it. All right, integral must end with an integration variable like dx. Okay. Okay, so I'm doing something wrong here. I don't know why, but it doesn't let me put D. Let's put D from here. So how's that? DT. Okay, well, it doesn't let me do that. So, folks, I'll figure out why. I should have looked at that more carefully before class, but I missed that. So I'll figure out why this is not working and I'll explain you. So again, it's very easy to do these integrals. It should be. I'm not sure why it doesn't let me do that, so I'll have to figure out what the problem is. But for the time being, I think we should be fine. So I'm going to stop the lesson here and we'll do more on that tomorrow. So tomorrow I'll start addressing this issue and then we'll calculate some area integrals. Again, we're very much towards the end of the term with this material. We covered what we needed to. So that's just a little bit of time left. This time that's left, we can use to experiment a little bit. I'm going to stop the recording here